5 separate animal groups evolved into crab-like body plans over the last 250 million years. Scientists call this carcinization, and the pattern is so consistent that researchers now predict which species will evolve crab features next. But the evolutionary advantage isn't what most people think. Crabs didn't conquer Earth through aggression or speed. They succeeded through defensive geometry. The wide, flat body plan with tucked legs creates the lowest profile possible for hiding in crevices while maintaining 360-degree awareness through elevated eye stalks. You can't ambush what sees in all directions while protected on 5 sides. True crabs belong to the infraorder Brachyura, with over 7,000 species identified, but at least 5 other groups independently evolved the same body structure. Porcelain crabs aren't crabs. King crabs aren't crabs. Hermit crabs that leave their shells and flatten out aren't technically crabs. They all discovered the same solution to the same survival problems. The process starts with elongated bodies. Lobsters, shrimp, and other crustaceans have extended abdomens that create drag in water and offer large attack surfaces to predators. Then, environmental pressure selects for shorter abdomens. Over millions of years, the tail section folds underneath the body, compacting the vulnerable rear into a protected chamber. The body widens to compensate for lost length. Suddenly, you've got a crab. But here's what makes carcinization different from other convergent evolution. Most convergent traits involve single features: wings, eyes, echolocation. Carcinization involves rebuilding the entire body architecture. Legs reposition, internal organs rearrange, muscle attachments relocate, the nervous system reorganizes. This isn't tweaking one system, it's reconstructing everything simultaneously. Hapalogaster mertensi shows the transition in progress. This hermit crab species started abandoning shells 15 million years ago. Modern populations have flattened bodies and reduced abdomens, halfway between hermit crab and true crab morphology. Genetic analysis from 2017 confirms the species is actively carcinizing right now, with populations in Alaska showing more crab-like features than populations in Japan. Then there's the mechanical advantage that explains the obsession with this body plan. Engineers at MIT published research in 2020 analyzing crab shell stress distribution under predator attacks. The curved carapace redirects impact forces toward edges and legs rather than concentrating stress on vital organs. A domed shell would crack. A flat shell would crush. The specific curvature crabs evolved distributes force optimally for maximum survival under biting attacks. You couldn't even target the legs effectively because crab leg joints position at angles that make them incredibly difficult to grip or break. When a predator grabs a leg, the crab can autotomize, deliberately snap it off at a predetermined break point, and regenerate it later. Losing a leg means surviving an attack. That's a trade worth making when the alternative is death. Talk about defensive innovation. The abdomen tucks so tightly underneath that most predators can't access it without flipping the entire crab over. But flipping a crab requires exposing yourself to those front claws for several seconds. Many predators decide the caloric gain isn't worth the injury risk. The body plan itself functions as a deterrent before combat even starts. King crabs demonstrate carcinization's power through sheer success metrics. Lithididae family evolved from hermit crab ancestors between 40 to 25 million years ago. Today, over 120 king crab species inhabit depths from shallow water to 6,000 meters. They range from 10 centimeters to 3-meter leg spans. The crab body plan scales across environments and sizes while maintaining effectiveness. But the evolutionary path isn't reversible. Once a lineage carcinizes, no species has ever decarcinized back to an elongated body plan. Scientists at Oxford analyzed 450 million years of crustacean fossils and found 0 instances of crab-like ancestors returning to lobster-like bodies. The transition functions as an evolutionary one-way street. Once you go crab, selective pressure keeps you crab. The eye stalk advantage deserves specific attention. Elevated eyes on mobile stalks provide vertical scanning capability while the body remains hidden in substrate or rock crevices. Predator detection range increases by 40% compared to fixed-position eyes. Prey detection improves similarly. This single feature, independent eye mobility, compounds the defensive advantage of the body plan itself. Porcelain crabs evolved their crab-like appearance from squat lobster ancestors around 50 million years ago. Genetic testing proves they're not closely related to true crabs despite looking nearly identical. They independently discovered that flattening the body and widening the carapace improved survival rates in intertidal zones where wave action and predator pressure create extreme selection forces. You couldn't hide effectively with an elongated body because crevice access depends on vertical clearance, not horizontal length. A 10-centimeter long lobster needs a 10-centimeter deep hiding spot. A 5-centimeter wide crab needs only a 2-centimeter gap. Crack coverage quadruples, while body mass remains constant. That's geometric efficiency predators can't counter. Then, 2019 research from the University of Florida revealed the developmental genetics behind carcinization. Multiple separate genes control different aspects of body plan: abdomen length, carapace width, leg positioning. But these genes share similar regulatory sequences, meaning environmental triggers can activate the entire transformation suite simultaneously, rather than requiring separate mutations for each feature. Evolution has a carcinization toolkit ready to deploy. Coconut crabs, the largest terrestrial arthropods at 4 kilograms and 1 meter leg span, show carcinization extending beyond marine environments. These hermit crab descendants abandoned shells completely and evolved hardened abdomens instead of tucking them. They didn't become true crabs, but they adopted key crab features for terrestrial success. The body plan works on land when properly adapted. The abdomen reduction creates another unexpected advantage. Less body mass in the rear shifts the center of gravity forward, improving stability on uneven surfaces. Crabs rarely tip over compared to lobsters or shrimp attempting to navigate the same terrain. Balance improvement means faster movement and better escape capability despite having shorter legs relative to body size. But defensive advantages only explain half the story. The crab body plan also optimizes offensive capability. Front claws position closer to the center of mass, generating more leverage and crushing force than claws positioned at the end of extended bodies. Biomechanical analysis shows crab claws produce 3 times more force per unit of muscle mass than lobster claws. Geometry amplifies strength. Stone crabs demonstrate this through specialized crusher claws reaching 19,000 newtons of force, powerful enough to crack open oyster shells and snail shells with single crushes. Modern human jaws produce around 700 newtons. This isn't size-dependent power. This is architecture-dependent force multiplication. The crab body plan enables predation strategies impossible for elongated crustaceans. You couldn't compete in shallow water ecosystems without carcinization advantages. True crabs inhabit every ocean zone, every temperature range, and every substrate type. From Arctic waters to tropical reefs, from sandy bottoms to rocky shores, the body plan succeeds everywhere. That's not coincidence. That's optimal design for crustacean survival, discovered 5 separate times through independent evolution. Modern carcinization research focuses on predicting which species might transition next. Squat lobsters show the most promising indicators. They're already semi-flattened with reduced abdomens. Several species demonstrate population-level variations in body proportions, consistent with early-stage carcinization. Give them another 10 million years under the right selective pressure, and we might witness the 6th independent evolution of crab-like bodies. That's the reality of why everything evolves into crabs. The body plan solves multiple survival challenges simultaneously: defense, mobility, predation, and stability through geometric efficiency that elongated bodies can't match. Evolution discovered this solution 5 times because the advantages are overwhelming once environmental conditions favor compactness over length. No modern predator evolved specifically to counter crab morphology. The design works too well.